Hello everyone. Today we are going to solve building teams problem from CSS problem set. Okay. So there are n pupils in Ulovis class and m friendships between them. Your task is to divide the pupils into two teams in such a way that no two pupils in a team are friends. You can freely choose the sizes of the teams. Okay. So the first input line contains two integers n and m, the number of pupils and friendships. The pupils are numbered from 1 to n. Then there are m lines describing the friendships. Each line has two integers a and b, pupils and friendships. Alright, so read the problem statement first. I will just summarize it. So we have been given here some nodes and edges. Like n represents the number of nodes and m represents the edges. Okay, so in the sample test case, here we have been given 5 nodes and 3 edges, and these are 1, 2, 1, 3, 4, 5. Here, uh, 1 and 2, there is edge between 1 and 2. That means 1 and 2 are friends. According to the problem statement, 1 and 2 are connected, thus they are friends. Then 1 and 3 are connected, then 4 and 5 are connected. Okay. So what the problem asks us to do is we will have to uh, divide from this graph. So from this graph we'll have to divide the node into two teams such that no common friends are in the same group. For example, let's represent this as group A and group B. Okay. So here 1 and 2 are friends, right? So 1 and 2 cannot be in group A. They will have to be in different groups, right? So that's the problem statement asks. So how we can divide this team? Okay, so suppose I put 1 in group A, then I can put 2 in group B, then I can put 3 in group B as well. I cannot put 3 in group A because then 1 and 3 will be in the same group, right? Similarly, uh, in this portion, in this component, this is basically a graph, right? This is one component and this is another component. So in this component, I can put 4, I think, anywhere. So let me just choose for group A. Then I can place 5 in group B. Okay. So here we can see that uh, in individual groups, there are no such nodes that they are friends. Like 2 and 3 are not friends, 2 and 5 are not friends. There's no S between 2 and 5, right? So given a graph, we'll have to divide them into two groups such that no group have common friends. Okay, so how can we solve this? Okay, so build the let's try to understand the problem from very base ground, right? So let's suppose we have just two nodes, 1 and 2. 1 and 2 is connected, right? 1 and 2 are connected, so we can just put 1 in group A and 2 in group B. Okay, suppose we had 1, 2, 3 like this. We have 1, 2, 3. This is the current graph. How can we put this? Okay, so now if we put 3 in group B, then it's a valid, right? But we cannot put 3 in group A, right? Okay, so this is a valid solution, but what if there was edge between 2 and 3? Okay, now 3 can be in group. If we put 3 in group A, right? If we put 3 in group A, then 1 and 3 are common, right? So we cannot, so this is an invalid. This is an invalid placement. Okay. Now let's suppose we put 3 in group B, right? So 2 and 3 are also friends. So this is also an invalid placement. Okay. So from this scenario, we can say that if there is a cycle, okay. So if there is a cycle, we cannot divide that scenario in that we cannot divide these nodes into two groups such that there are no common friends, right? So can so in this kind of scenario we will have to print impossible, right? Okay, so now from this test case we understand that if there is a cycle we cannot find a valid solution, but does this avoid any cycle? Okay, so here we have odd cycle, right? Now let's see a scenario where there is an even length cycle. For example, 1, 2, 3, 4, right? So there is a cycle and it's even length, right? So suppose I put 1 in group A, then I will have to put the next level connected in different groups, right? So I put 2 in group B, 4 in group B. Now, as 4 and 3 and 3 and 2 are connected, I cannot put 3 in group B, so I'll have to put 3 in group A, right? So I put 3 in group A. So now A has 1 and 3, B has 2 and 4. So 2 and 4 are not directly connected, 1 and 3 are not also directly connected. So this is a valid solution. So from this scenario, we can see that if there is a odd length cycle, we cannot place them, we cannot find a valid solution. But if there is any even length cycle, then we can find a valid solution. So we have seen the cycle test case now. Now let's see a general case. Okay. So if there is no cycle, just a random graph, right? Let's suppose a random tree. Okay. So now can we find a value solution? So I can place one in group A. I can place one in group A, then 2 and 3, then 2 and 3 in group B, then 4 and 5 in group A. So in any other scenario, we can easily find a value solution. Okay. So now can you find any similar scenario here? If you have done any if you have learned any graph algorithms, any standard graph algorithms, you can easily find that this is a bipartite scenario. Okay, so this is basically a bipartite graph. Okay, so I hope you know what bipartite is basically. Okay, so basically, given a graph, if we can color that, given a graph, if we can color each node in two colors such that they are not two colors such that uh, the parent and child are of different color. For example, here one is parent and B is child. A and B is different. Similarly, one is parent and two is child. So one and two are different. For example, in this subgraph, 2 is parent and 4 is child. So 2 is in group A, group B, and 4 is in group A. So we can color them differently. So this is how we can find a bipartite graph. So basically, we'll just have for this problem, we'll just have to check if the graph is bipartite or not. If it's a bipartite graph, then yes, there exists a valid solution. Now, if the graph is not a bipartite graph, then we will just have to uh, output impossible, right? Okay, now in the problem we will also have to print the valid group, right? Okay, so this is for node 1, node 2, node 3, node 4, node 5. Okay, for every group, for every node we will have to print their group. Okay, so we can do that in implementation also, but with just some tricks. Okay, let's see the code now. All right, so at first I have just taken the input, the name and the ages. I have just in this question I have just taken the input. Then in this question I have basically implemented the graph. All right. So I have declared the answer array at the beginning. These are just standard procedures. Now in the DFS algorithm, first of all, I am just checking every connected components, right? So I am just going through every component now. if it's the first node of the component, like for example, in the given graph, in the test case, uh, for example, if I am starting with node 1, from node 1 I am starting DFS, right? So the starting node I am setting it to group 1. I am marking it as group 1. So here you can see answer of current node is equal to 1. Then I am just running a DFS algorithm here and visiting all the other nodes. Okay. So now what's happening in the DFS algorithm is that, okay, so this is a standard DFS algorithm. Here I have the node and parent parameter. Okay. So here I am just doing a cycle check, right? So if it is equal to parent, that means the current child. If the current child and parent is same, that means I have just visited this node. Like, it's just a standard procedure to avoid loops. I hope you know all of this. Now here is the main part. Okay, so if the current child, okay, so if the current child is not visited, I'll have to color it, right? I'll have to visit it and color it and call a DFS from here. Okay, so how will I know what color I will have to choose here? So what I have done is, suppose I am starting, sorry, suppose I am starting the DFS from here, right? So now from here, I can see if the node 1 is colored to group A, then I will color all the childs to group 2. Okay, basically I will include all the childs to group 2. Okay, so if answer of node is equal to 1, then I am just doing answer of child to 2, else else I'm putting it into 1. This is just a ternary operator. I hope you know all of this. Then I'm just calling DFS from here. Now if the node is visited, right? If the node is visited and the color of child, if the node is visited and the color of child is equal to the color of node, that means there is an odd length cycle here, right? So for this case, right, see here, suppose I have colored it to group 1, group 2, group 2, right? Okay, so suppose I'm started from a DFS from here. Now I will just go here, then from here I can go to here, like from the recursion tree you can see. Now from 3 I have got my child, I have got the child as 2. From 3 I have got the child 2, right? So the 2 is in group 2 and the 3 is also in group 2. That means the color of child and the color of parent is same. So if they are same, then I am just making the flag as true. This flag represents that there is a cycle. Okay, so this means there is a valid cycle. Okay, so if it is a cycle, then I will just have to print impossible. Okay, so in the graph, if there is a cycle, I will just print impossible. Otherwise, I will just print the answer that I calculated. All right, so this is the solution. Okay, so that's it for today.